Good morning. This is your stat sensei, Mr. Spensei, going over a pre-quiz that we just took. All right, so we have a probability of A equals 0.3 and the probability of B equals 0.5. What is the probability of A union B if A and B are independent? So the very first thing, independent. Probability of A and B equals the probability of A times the probability of B if independent. That is not on your formula sheet. You have to memorize that, right? But they also have the A union B, and that is on your formula sheet. And that says the probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. Well, they just told us they were independent. And since they're independent, it's independent, I can substitute probability of A times B for this. So I'm going to go ahead and do that. And now I have the probability of A union B equals the probability of A plus the probability of B minus the probability of A times the probability of B. All right. And then at this point, I can start plugging in. Well, they've given me 0.3, and I can plug that in here, 0.5 here, and 0.3 and 0.5. So here we go. 0.3 plus 0.5 minus 0.3 times 0.5. Now I'm going to tell you on the test, we're going to be looking that you've written this and that you've written this. So you're going to have both of those things, all right? So make sure you get your points, and then you're going to have to show your substitution where you plugged in your numbers, which I just did here. So in this case, 0.3 plus 0.5 gives me 0.8 minus 0.15, that's this times this. So the probability of A union B equals 0.8 minus 0.15 or 0.65. All right, continuing on. And now we have the probability of X equals 0.35, the probability of Y equals 0.4, Y is 0.4, and the probability of XY is 0.28. What is the probability of Y given X? Well, this is just a puzzle, and so I need to start off with whatever the probability of X given Y is. Well, the probability of X given Y is on your formula sheet, and that's the probability of X and Y over the probability of Y. So I'm going to plug into that, and I end up with 0.28 equals, and I don't have X and Y, so this I'm just going to probability of X and Y over 0.4. I need to get that out of the denominator, so I'm going to multiply both sides by 0.4. And when I do that, I find out that 0.112 equals the probability of X and Y. So I now know the intersection. All right, please don't forget that this is a given. Now they have the probability of Y given X. So the probability of Y given X equals the probability of X and Y all over the probability of X. So I can plug in, and what do I have? Well, I know 0.112 equals 0.112, and they told me X is 0.35. So the probability of Y given X is just 0.112 over 0.35. And that happens to turn into a decimal. And by the way, we need to see all of this work. So the probability of Y given X equals 0.32. All right. Given the probabilities A equals 0.3, A union B is 0.7, what is the probability of B if A and B are mutually exclusive and if they're independent? So here we're asked to do two questions. One we're asked to do if they're mutually exclusive and one if they are independent. Well, once again, they give me this, I need to be writing my general addition rule, which I can find on my formula sheet. My formula sheet says the probability of A union B equals the probability of A plus the probability of B. So everybody should be writing down that formula. All right, A and B. Well, let's do the mutually exclusive first, which happens to be the easier one. And we know what A is. We don't know what B is, but we know A union B is 0.7. So plus the probability of B minus, now they didn't tell us the intersection, but they told us it was mutually exclusive. Well, mutually exclusive is when we have a Venn diagram with no overlaps. So here we have no overlap, so we're subtracting out 0. So in this case, 0.4 equals the probability of B. And all I did was subtract 0.3 from both sides. So that's the answer to the mutually exclusive one. The independent one is a little more complex, but we have to remember the probability of A and B equals the probability of A times the probability of B if independent. Now, once again, that formula is not on your formula sheet, and you need to write it down. You're going to have to memorize that one. But then we also need to write down our general addition rule, which is the probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. Once again, just like above, I'm going to substitute this in for the independence because I don't know what that intersection is, but I do know that they told me they're independent. So I have the probability of A union B equals the probability of A plus the probability of B minus the probability of A times the probability of B. So I'm going to start plugging in, and A union B is 0.7. A we don't know, so this is 0.3. And I'm just going to just call that a B just to make it easier. Minus 0.3 times B. Because once again, we don't know B, but we have all this. So I'm going to subtract 0.3 from both sides, and now I have 0.4 because I subtracted 0.3 from both sides. And I have equals B minus 0.3B. Well, what's 1B minus 0.3B? Well, that's 0.7. So 0.4 equals 0.7B. If I divide both sides by 0.7, I end up getting B equals 0.4 over 0.7, which equals 4 sevenths. And so there's my answer for that one. All right, the next one. Probability of E equals 0.45, probability F is 0.32, and UF is 0.626. Are E and F independent? All right, so we have a couple things here. They're asking for independence, whether or not they're independent. And they also gave me, hey, here's my, I'm probably using a general addition rule. So we'll start off with that. The probability of E union F equals the probability of E plus the probability of F minus the probability of E and F. But we're checking for independence, and I don't know what this is. They didn't tell me this. So I need to figure out what that is. But if they're independent, then once again, the probability of E and F equals the probability of E times the probability of F. Once again, that's true if independent, only if true then. So I can plug that in. So I'm going to go ahead and plug that in. I'm going to substitute that in, and I'm going to have probability of E union F equals the probability of E plus the probability of F minus the probability of E times the probability of F. All right. So when I plug in, I end up getting 0.626 equals the probability of E is 0.45 plus 0.32 minus, and now I'm plugging in 0.45 times 0.32. All right. So when I multiply these two together, I end up getting 0.144. So 0.626 equals, add these together, 0.77 minus 0.144. When I subtract these two, I get 0.626 equals 0.626. This is a true statement. And so because this is true, events E and F are independent. And by the way, I have to make the statement. Events E and F are independent. Now, there's more than one way to approach this problem. Another way would have been just to say, you know what? So all I did was plug in because this had to be true. Another way would have been, well, probability of E union F equals the probability of E plus the probability of F minus the probability of E and F. And I just wrote the general addition rule and I plug in. And it's kind of important to be familiar with all these methods. Equals 0.45 plus 0.32 minus the probability of E and F. So 0.626 equals 0.77 minus the probability of E and F. And I solve, and I end up getting negative 0.144 equals the negative probability of E and F. So that tells me when I solved it this way, that, and make both sides positive, that E and F equals 0.144. Well, checking out by the multiplication rule, probability of E and F equals the probability of E times the probability of F. So that means 0.144 has to equal 0.32 times 0.45, and 0.144 equals 0.144 events E and F are independent. We could also have checked this out by the general addition principle. Not general addition by conditional probability, but I'm going to skip that for this particular assignment. All right. So there's a couple ways to approach it. There is still a third way, and there's probably a fourth way as well. But these are what I would have recommended, and you should be familiar with both methods of doing it. They're very similar. All right. A grocery store purchases melons from only two distributors. We have distributor J and we have distributor K. All right. So we have a distributor. J provides melons from organic farms. The distribution of diameters of the melons from distributor J is approximately normal with a mean of 133 and a standard deviation of 5. A randomly selected melon from distributor J has a probability of 0.21 of having a diameter greater than 135. Distributor K provides melons from non-organic forms, which are normally distributed with a mean of 144 and a standard deviation of 7. The probability is, there's our probability, 0.84 that the melon randomly selected from K will have a diameter greater than 138. So this is greater than 138. For all the melons at the grocery store, 70% of the melons are provided by distributor J, and the rest by distributor K. And it tells you right away we want to do a table, but I would have known that we were doing a table because I'm working with two variables and I have three problems. My two variables are my distributor, who my distributor is, and then of course my melon size, whether or not they're greater than 133 millimeters. All right. So let's take a look at this. So when I look at this problem, it's like, well, I need a table, and I need to define variables. So let J or let PJ equal the probability a melon came from distributor J. By the way, we are going to be looking for this on your test. Let PK equal the probability a melon came from distributor K. And then we have the melon sizes, which are greater than 138 and less than 138. And I'm just going to use greater than 138 and less than 138 when I make my table out. So I'm going to make my table on a separate sheet of paper, at least I hope I am. I'm drawing my table, and I need to go back and identify the variable associated with only one number. And this needs to be a fairly large table because we got some small numbers to work with. All right. And so greater than 138. So here we go. All right. So when I read this, 0.2, J has a probability of, so coming from J, so this has from J and greater than 138 is 0.21. So that has two variables. It has the distributor and the melon size. Probability 0.84 that a melon selected from distributor K will have a diameter greater than 138. So this is the distributor and the melon size. So once again, two variables. Then I have, for all the melons of the grocery store, 70% have from distributor J. Oh, so there's my 0.70. It's associated with only one variable, and this is 0.30, and of course, a really difficult number of 1. So this is J, and this is K. Make sure that you've already defined them, which I already did. All right. And this is going to be probability. This is going to be melon greater than 138. And I can either use a variable or I can write it out. So I can use some other variable. And then I can say melon less than 138. Once again, I could use the variable, but if I use a variable, I have to define it out. So I just chose to write it out on this one because I thought it'd be shorter. Now, remember, we bring these numbers up, write them small. So this becomes 0.70 and 0.70. And this is 0.30. And this is 0.30. All right. So a randomly selected melon from distributor J has a 0.21 of being greater than 138. So this is going to be 0.21 right here. And this is 1 minus 0.21. And when I multiply those out, I end up getting 0.147 and 0.553. And these two values should sum up to 0.70. When I go to the next one, which are normally distributed with a mean of 144, the probability 0.84 that a melon selected for random from distributor K will have a diameter greater. So once again, we're in the greater, so distributor K and greater, so this is going to be 0.84. And this is 1 minus 0.84. This times this gives me 0.252. And this times this gives me 0.048. And this value plus this value equals this one. And then we sum across, and I end up getting 0.399 and 0.601. So that should be my values. Okay. All right. For a melon selected at random, hold on a second while I make an adjustment so I can read this. For melon selected at random from the grocery store, what is the probability the melon will have a diameter greater than 138? Oh, that's easy. So probability, and once again, we have to have this introduction. So the probability, the diameter. I did not write that well. Probability that the diameter is greater than 138. So we need to have that, defining what it is. And probability the diameter is greater than 138 is 0.399, straight off the table. Very easy to read. All right, the next question. Given that a melon selected at random from the grocery store has a diameter less than 138, we have a given. What is the probability that the melon will be from distributor J? All right, so we want the probability, the probability that J, given that it's less than 138. Well, oh, I'm sorry, I wrote that wrong. It's the probability, given that a melon is selected from random has a diameter. Oh, no, that's correct. The given is the denominator. So the probability that J given less than 138. So in this case, what's the probability that it came from, or the probability that it's less than 138? Well, the probability that it's less than 138 is 0.601. So 0.601 goes in the denominator. And less than 138 and came from J. So I'm looking to go, well, this, and then here's my intersection. My intersection is 0.553. So 0.553 goes in the numerator. And then this equals, when I divide it out, 0.92. The next one, what's the probability that a randomly selected melon has a diameter less than 138 and was from distributor K? So in this case, we're not looking for anything that's given because there's no given, but we want it to be less than 138. So we're looking right here at this group and from K. So we're looking for the probability that it's less than 138 and from K. So we're looking for that intersection. And that just happens to be something we can read straight off the table, which is 0.048. Once again, we have to have this every single time. So that's why it's really important to define your variables, just like we did above at the very beginning. Given that a randomly selected melon came from distributor K, what's the probability it has a diameter greater than 138? All right, notice we have a given here. Well, we're given that it came from K, so the probability, we're looking for the, excuse me, why do I keep doing that? The probability randomly selected melon has a diameter greater than 138. So this is going to be my denominator. So K will be my denominator, and greater than 138 is up here. All right. So probability greater than 138 given K equals, well, the given was K, so that's 0.30. And now we're looking for this intersection because we need to be greater than 138. So 0.252 over 0.30, and that equals 0.84. Probability of greater than 138 given K. All right. Next thing. The distribution of melons of the diameter from K is approximately normal with a mean of 144 and standard deviation. The distribution are independent. Ooh. Important phrase. What is the mean differences? All right. Wow. Well, I just sit there and I see, hey, right here it tells me it's 144. That's from K. And I go back all the way up here and they tell me it's 133. Well, that means I can just go, well, 144 minus 133 equals 11 millimeters. So on average, we would expect a mean difference of 11 millimeters. All right, on average, we expect. So I need to show this work and this work in order to receive credit. And so what's the standard deviation of K minus J? Well, they told me K is 7 millimeters and J had 5 millimeters. So in this case, we're all right, standard deviation of K minus J would equal the standard deviation of 7 minus 5. Well, excuse me, it wants me to go 7 minus 5, but I can't do that. I have to come back and I have to square them, add them. So square root, so this becomes 49 plus 25 equals the square root of 74, which is approximately 8 0.6. All right. So that would be my answer for this one, and that would be work shown. I should show all of that. Finally, we're heading on to the famed pinata problem. A pinata is a container filled with toys and candy is broken open by hitting it with a stick. The drawing shows Sophia trying to break a pinata. The probability she'll break the pinata on the first hit is 0.2. She'll continue to hit the pinata until it breaks. If she does not break the pinata on a particular hit, the pinata is weakened, and the probability she'll break it on the next hit is 0.2 greater. That means the probabilities are changing than the probability on the previous hits. For example, the pinata first hit probably will break on the second hit is 0.4. And the reason that is we started off at 0.2 and then it didn't break. So that we had to add another 0.2 because it's 0.2 greater. So the probability to break on the second hit is 0.4. Calculate the probability that Sophia does not break the pinata on the first hit and does break it on the second hit. All right. So we're going to not break it on the first hit. So I have not break times break. Well, not break would be 1 minus 0.2 because that's 0.2 is the probability of break. And the second one is going to be the 0.2 plus 0.2 because they said it was 0.4. So this equals 0.8 times 0.4. So the probability that she breaks it on the second hit is 0.32. All right, let the random variable x represent the required number of hits. And by the way, notice they defined a variable for us for Sophia to break it, the pinata, complete the probability distribution in the table below. All right, so the probability that it breaks on the first hit is 0.2. The probability it breaks on the second hit, we've already done that. So we've already done those, but and now I need to do 3, 4, and 5. Well, so the probability of the first one is 0.2. Then it's going to be, well, 1 minus 0.2, and then times 0.2 plus 0.2, not break and a break. All right. Then I have to have the third one means not break, break. Well, the probability of it not breaking is still 1 minus 0.2. That's that 0.8. But what's the probability that it doesn't break on the second one? Well, that's 1 minus this. Well, this was 0.4. So this is going to be 1 minus 0.4. All right, which happens to be 0.6. But the probability is 0.2 greater. So now it's 0.2 plus 0.2, plus another 0.2, which is also 0.6. So we're going 0.8 times 0.6 times 0.6, and this equals 0.288. So that's the probability it breaks on the third one. Then we have to have not break, not break, not break, and a break. Let's do the breaks first because they're easy. We're just going to add another 0.2 to it. 0.2 plus 0.2 plus 0.2 plus 0.2. And we see we have an 80% chance of it breaking on the fourth one now, given that it didn't break on the first one. Well, once again, this is 1 minus 0.2. That's that 0.8 that we had. Then this is 1 minus 0.4, which gives us 0.6. Well, it can't break on this one, so this has to be 1 minus 0.6, because this is 0.6 up here, and 1 minus 0.6 is 0.4. So I need to multiply 0.8 times 0.6 times 0.4 times 0.8, and I end up getting equals 0.1536. And then finally, on the fifth hit, so we have not break, not break, not break, not break. Didn't break on the first four, and then it breaks on the last one. So on the last one, we're just adding to that. So 0.2 plus 0.2 plus 0.2 plus 0.2. So 1, 2, 3, 4, and then the fifth one plus 0.2. Well, guess what? That sums up to 1 whole. All right, it sums up to 1. So the probability of not breaking on the first one was 1 minus 0.2. That hasn't changed. That's 0.8. The probability of not breaking on the second one is 1 minus 0.4. So that's 0.6. That hasn't changed. The probability of it not breaking on the third one is 1 minus 0.6. So that's 0.4. So that hasn't changed. And then on the last one, it's 1 minus 0.8, which is that value right there, and that gives me 0.2. So once again, multiply all those together, 0.8 times 0.6 times 0.4 times 0.2 times 1, and that equals 0.0384. And if I sum all of these together, they sum to 1 whole. All right, the next thing said, calculate the expected value. Well, even if you'd messed this up, you still could have gotten points here by showing your work. You say, hey, you know what? I'm going to fill in values that sum to 1, whatever they are, and then I'm going to go, well, I can get points here. And so in this case, showing my work would be the expected value of x, and they've already defined it for me, so I don't have to. Would be 1 times equals 1 times 0.2 plus 2 times 0.32 plus 3 times 0.288 plus 4 times 0.1536 plus 5 times 0.0384. All right. And when I do that, I end up getting an expected value of 2.5104. Now, here it says interpret in context. Normally, we're not going to tell you that. You just have to do it on your own. So on average or in the long run, I'm going to do in the long run. I could have done on average. In the long run, we would expect it to take an average of 2.5104 hits to break this type of pinata. All right. Thank you for watching, and that covers up for our entire video. I hope this was helpful. Oh, lastly, please make sure you define all your variables when you're working with probability. We're going to be really strict on that on the test. Thank you.